Let's look at example C here. I'm going to leave this example B for you to try. Okay. All right. I'm going to go to example C here, where we have the indefinite integral of 7 over x plus the square root of x dx. All right. Instead of separating it like this, I'm just going to leave it all as one integral. Just because we can separate it doesn't mean that we always have to, okay? Sometimes it makes things simpler for us, but here I'm just going to leave it all the same, right? When I look at this integral here, actually, I'm going to separate it. I'm sorry. When I look at this integral here, I'm going to look at each piece since I'm starting out, right? I know I have a bunch of these antiderivative formulas, right? And one of them involves an x in the denominator. And so I have to be on the lookout for that. Now, it doesn't say anything about a 7 being in the numerator, but 7 is like a constant. So I can bring that out in front of my indefinite integral. In addition, when I have a square root, there didn't seem to be a rule related to a square root, but it did have a rule that was the power rule that was related to x to a power. And so what I'm going to do is I'm going to rewrite this as x to the 1/2 power instead of writing it as the square root of x. And now I can see that these two antiderivatives, or these two integrals, have integrands. I didn't talk about this before, but these things that we're taking the antiderivative of are called integrands. Integrands. But these integrands looks like something from our actual rules that we went over earlier. All right, when I have the integral of 1 over x dx, that is the natural log of the absolute value of x. And when I have x to a power, what I do when I take the antiderivative is I add 1 to the exponent, and I divide by that same exact exponent, and I have plus c. Now, one thing that you should note here is that this is 3/2, as well as this denominator is 3/2. And so I could simplify this as saying x to the 3/2 over 3/2 plus c. Now, what most of you would like to do is when we divide by a fraction, you multiply by its reciprocal. And so it's probably a little bit better to rewrite this as 2/3 times x to the 3/2. Because remember, when we divide by a fraction, we multiply by its reciprocal. And so that's the way I'm going to write this. I'm going to write it as plus 2/3 x to the 3/2, and then plus c. All right, I'm going to start part D for you guys, and I'll have you guys finish that yourself. I'm going to rewrite some things here. This is just an integral of 3x to the 9th. Whoa, I have an x in the denominator. Now, I know I have a rule for 1 over x in the denominator, but that one always has a power of 1. If there's ever a case where you don't have a power of 1, then you can't use that rule there. And so what I'm going to do is I'm going to rewrite it as x to some exponent, because I can always bring an x out of the denominator by making its exponent negative. And so this is going to be plus, well, when I have the cube root of a variable, it's that variable to the 1/3 power. But I brought it out of the denominator, so I've got to make it negative. All right? Plus 8 times, well, I'm going to bring that out of the denominator because I can't use this rule here because there's not a 1, there's a 3 as the exponent in that x in the denominator. If I bring it out of the denominator, the exponent becomes negative. All right? And now I want you to finish this. All right? We're going to look at a few more examples. I want to look at example F. I'll have you try example E. It's easy. Easier than some of these others. And I'm going to have you try this one here, G. All right? And we're going to look at F and H. F is a little bit more difficult because there's some things that we need to think about. Okay? I just want to do a quick review, for instance, right? In this integral here, my integrand has e to the 5t. Now, I'm going to think back to our days of taking the derivative, which isn't far away, right? If I were to take the derivative of e to the 5t, right, with respect to t, I'd get e to the 5t, and since that's not just a t sitting there, it's a 5t, I've got to use my chain rule and multiply by the derivative of 5t with respect to t, which is 5. Okay? So when I try to think of antiderivative, I've got to think of undoing what I would do if I did the derivative. So I'm probably not going to multiply here by 5. There's probably going to be some sort of a division by 5. Okay? Let's look at this example now. That 4 I can bring out in front of the integral, and I'll look at integral of e to the 5t dt. Okay? Now, I said on that earlier in this lecture, I probably used x, but the integral of e to the t dt is e to the t plus c, right? Because if I do the derivative of e to the t, I'm going to get back e to the t. So this one's nice, right? And so my antiderivative is sort of going to be the same, but when I don't just have a t there and I have a constant there, when I take the derivative, I normally have to multiply it by it. So when I take the antiderivative, I've got to undo that multiplication that will end up happening. So I'm going to divide by that constant that's multiplied by t there, and I'm going to add a plus c for my family of antiderivatives. Now, this is weird, so I'm going to check it. I'm going to do the derivative of this thing right here of my answer, right? Well, my 4/5 is going to stay out there. I'm going to do the derivative of e to the 5t, which is e to the 5t. I have a chain rule, multiplied by 5, because that's the derivative of that part. These 5's cancel, and I'm left with 4e to the 5t. Note, the derivative of the c here would be like putting a plus 0 there. I didn't decide to do that. Okay? And so when we have a constant multiplied in our exponent here, we divide, or we undo what we do with the chain rule by dividing by that constant. Okay? Last but not least, and I just put this one on here because it's interesting. Okay? Note here I have the indefinite integral of 2y squared dx. Notice here that my integrand involves a variable that I don't integrate with respect to, right? Here, I want to integrate with respect to x, not y squared. This means y squared is a constant. It's just like having a number 5 there, but it's written as some letters, right, as a variable. And so what I can do to do this integral right here is I can bring that 2y squared out. And there's always a 1 understood to be there, right? 1 times anything is that anything, right? And so I have 2y squared times the integral of 1 dx. Well, the integral of 1 dx, 1 is a constant. I want to know what function has a derivative equal to 1. Well, it's the function x. And then I have plus c. Note, if I do the derivative, and this is going to look very weird to check myself. If I do the derivative with respect to x of 2y squared x plus c, but we know that's going to equal 0, this x is a constant. No, this x is not a constant. This x is a linear term. And the derivative of my linear term is the number that's multiplied out front. Since y is a constant, it's like a number. I get the 2y squared. All right? And so there we have it. This one's weird. When you do if you ever get in the case where the variables inside of your integrand are not the variable you're taking your integral with respect to, then all of those variables are going to stay in your final answer. And you do the derivative as you normally would using the other rules. All right? This concludes what we have for this section. I hope you found this video valuable in helping you learn about what an antiderivative is, as well as an indefinite integral. We'll pick up with this and look at some of the examples that you tried in class when we meet again. Have a great one.